Okay. So, today I would like to speak about infiltration, modeling infiltration in general in hydrology. And infiltration is usually an important component, an important process that is to take into account when applying rainfall and off modeling. For instance, you may remember that for the time area method and the linear reservoir, I mentioned that the runoff coefficient that is to be estimated in order to compute the net rainfall, which is the part of the rainfall that directly contributes to the formation of the river flow. And estimating the runoff coefficient means, in practice, to estimate infiltration, because the part of rainfall that does not contribute to the formation of river flow is rainfall that is evapotranspirated and also infiltrated. Because, of course, there is a part of infiltrated rainfall that goes back to the river, but there is also part of infiltrated rainfall that doesn't go back to the river in a short time step. Maybe it goes back, but it goes back in a very long time frame. And therefore, for the purpose of rainfall and off modeling, it can be considered in many cases lost. Rainfall that does not contribute to the formation of river flows. Therefore, estimating the runoff coefficient means to estimate the rainfall that is lost for evapotranspiration, but also the rainfall, the part of rainfall that is lost because it infiltrates and doesn't go back to the river in a short time frame. This means understanding how infiltration works. Means to try to decipher what happens to infiltrated water, namely, if you want to be very detailed, to write a mathematical model for representing the infiltration process. So you can understand that infiltration is an important component in rainfall modeling in the hydrological cycle. Very often we deal with infiltration by using simplified approaches, like, for instance, the runoff coefficient, which is an empirical coefficient that takes into account the whole part of rainfall that is lost. Also, if you remember about the IMOD model, IMOD uses a simplified approach to take into account infiltration. It assumes that, in particular, that the watershed is able to store part of the water for infiltration, and this water is kept into the watershed and then evapotranspirated during dry periods. This is what IMOD does, what IMOD assumes. In the area that are not saturated, all the rainfall is infiltrated and subsequently evapotranspirated. So this is again a simplified approach to account for infiltration. But of course, if you want to be more detailed, if you want to use more details in representing the hydrological cycle, you have to use more complicated model for infiltration. Therefore, today I want to speak about the infiltration process, what happens actually in reality, and how we can model this important process. The first part of this lecture, about the first half, is not included in my slides. I apologize for this, because I decided just recently to be more detailed with respect to last year. And therefore I will pay particular attention to go very slowly, because it's quite a nasty part, it's a bit mathematical, so I will be very slow. And please, if you need any clarification while I'm lecturing, just be sure that you understand what I'm doing. I'm working on the blackboard, no PC, and the second part instead is included in my slides, but I will try to work on the blackboard today anyway, okay? So, let's talk about infiltration. What is infiltration? It's quite intuitive to understand what it is. When it starts raining, especially after a long dry period, you have the soil that is dry, and therefore we well know that a dry soil, if it is permeable, is capable of absorbing water. And this is the process that is called infiltration. Usually, infiltration is taking place in an unsaturated soil. So we are talking about water movement within the soil in condition of no saturation. So infiltration is different with respect to the movement that you have in groundwaters, where typically, when you refer to the movement and the dynamics of the water table of the falda in Italian, typically you refer to water that moves into a saturated soil. Instead, when we speak about infiltration, usually we work in condition of soil that is not saturated. Therefore, as I said, when it starts raining, the soil, if it's permeable, absorbs some water. It possibly gets saturated in the first layer, and then water moves in the vertical direction, mainly in the vertical direction. We consider this movement a monodimensional movement because we neglect any movement of water in the horizontal directions, x and y, but we just consider the movement in the vertical direction, z. And so, as I said, water starts moving in the underground, and eventually, after a very long time frame, the soil can get saturated. I said very long, but actually the time to saturation depends on the height of the soil and depends on porosity. So first of all, let me introduce some basic definitions. And first of all, I define the porosity of the soil. Let's call it PR, as the ratio between the volume of empty spaces in the soil over the total volume. I think we can use in English the term volume of voids, but I'm not sure. But I think you understood. It's the volume of the empty spaces occupied by air in a dry soil, volume of the empty spaces in the soil over the total volume of the soil. And this ratio, of course, varies between 0 and 1. It can be 0 if the soil is compact. It can never be 1 because it means that, of course, there is no soil, so it wouldn't be a meaningful definition. It can be 0 because if you have compact soil, the volume of voids can be 0. And let me define now the soil moisture. The soil moisture, theta, is defined as the volume of water over the total volume of soil. And theta is varying between 0 and porosity. I put a lower and equal sign here, but recent investigation have shown that it's once that you get some level of soil moisture, soil humidity, it's almost impossible to completely dry the soil. You can get complete dryness only if you put the soil in an oven and you heat the soil at a very high temperatures, because there is in Italian I would say a small pellicola of water, a small slide of water that remains attached to the soil particles, and with the only action of the gravity forces you cannot dry it. And also I put as upper limit the porosity, but it's impossible to get with the soil moisture to the value of porosity, because there are some voids in the soil that are isolated always. A fraction of voids that can be greater or minor, but there is a fraction of soil that cannot be reached by water because of the meanders that can be followed by water in the soil sometimes are blind, and therefore there are some voids that have no direct connection with the others and cannot be reached by water. Okay, but it's very important that we keep into account what is soil moisture in relationship with soil porosity. So what happens when it starts raining? Let's try to represent in a very simplified diagram where you have the ground here and you have here the vertical direction and here the soil moisture varying between 0 and let's say here. And let's suppose that we want to represent along the vertical direction. I put a minus z here because I assume the positive versus of the vertical direction upward. So I get the positive z upward, while I take as negative z's the ordinates that go into the underground. Okay, so I put negative z here. And let's try to represent by assuming that there is a rainfall event here, what happens to soil moisture along while we move along the vertical direction downstream in the underground. Okay, so basically what you get if the rainfall event is strong enough, you get a first layer of soil that is saturated, and this is called saturated zone. And then we get to a point where the soil is not saturated anymore, and therefore you have the soil moisture that is rapidly decreasing, and then experimental observation have shown that it gets almost constant for a long way underground, and this is a transmissivity zone. Then you get to a point where the humidity suddenly, the soil moisture suddenly decreases and goes towards 0. And this bend in the curve identifies what is called the humid front. Let's put a dotted line to show the border between the saturated zone and the transmissivity zone. Of course, as the rainfall event goes on, you get a lowering of the saturated zone, so you get a configuration like this, for instance. You may have or have not an impermeable layer confining the soil underground. Usually you have it, but sometimes it's very deep, sometimes it's close to the surface. If it's close to the surface, of course, you may get more easily to the condition of complete saturation. This is what happens if you have a long depth that is permeable. Also, you may have changes in permeability while going underground, and if you have changes in permeability, of course your curve can change its shape, because changes in permeability usually are given by changes in porosity, and therefore if you have a sudden change in porosity, this induces changes in the soil moisture profile also. But what is important for us is just to get an idea of how it works. You understand that modeling this phenomenon is not easy, because we have to deal with the two phases movement of water, because we have a mixture between water and air in the part that is not saturated. And this is difficult to represent, because when water gets in contact with the atmosphere, with air, you have also the capillary forces that are acting. You may remember what is the capillary force. You may remember, for instance, if you studied the principle of the communicating tubes, maybe in the high school, you know that if you have two communicating tubes or pipes, I don't know how to better say in English, and you put water here, you have studied that the level of water for the hydrostatic law gets to the same level, to the same height in the two pipes. But if you have a very small pipe here, then the level of water in the smaller pipe tends to reach a higher level because of the effect of the capillary forces, which is a kind of force that develops between the interface between air and water, which develops between water and the walls of the pipe. And it's a kind of attraction that the pipe exerts on water. And this kind of capillary force acts only when the way where the water is stored is very small, and this is the case of soil because you have pores where water is traveling, so they are very small, and only when there is an interaction between water and air, and this is the case of unsaturated soil. So you have this phenomena to take into account. And in the case of infiltration, the capillary force tends to attract water in the underground direction, so in the negative Z direction. So it takes water in more deep with respect to the situation in which you don't have the capillary force. And the capillary force is very significant. When the pore gets very small, you have a very strong effect of the capillary force, so you have to take it into account, which is, of course, not easy. And also, another reason that makes the process very complicated, it's also quite understandable, is that you need to specify the boundary conditions given by rainfall here. So you have to specify the full shape of the rainfall event, because you have to understand whether or not saturation is induced here, as I depicted in this picture. Because of course, if you have just a couple of drops of water, it gets infiltrated without giving rise to saturation. But if you have a lot of rainfall falling, of course you get saturation. But you have to understand this. So you have to specify rainfall in any point of this interface between soil and atmosphere. You have to specify rainfall in any point here. Of course, you can assume some simplifying assumptions, but it's complicated. And also you have to specify the boundary condition in the underground. So porosity, and if you have an impermeable layer, you have to specify what it is. So it's not easy. And you can already understand that one thing is try to understand how it works and to set up a theoretical model that is theoretically correct. Another thing is to apply the model in practice. So you can already understand that I will provide a theoretical explanation of this process, but at the end, of course, I will introduce some assumptions to make us able to apply to model infiltration in practice. So this is indeed the structure of this lecture. First, a theoretical development, and then the treatment of some simplified models that are currently used in practice, which are a bit more complicated than what we used so far in IMOD and linear reservoir, but they are not as detailed as the theoretical development that now I will try to derive and to explain to you. Okay, so let's try to describe this process mathematically. And a first equation that I can apply is conservation of energy. This is, as I said, conservation of energy is always satisfied in fluid mechanics, and therefore, even for describing this process, I can apply conservation of energy. And let me define energy of water. In general, how would you define, with respect to an horizontal plane of reference, if you have a particle of water here, which is not moving, how would you define the energy of this particle of water? Just by saying that the energy H for unit weight of water is given by the height, lowercase h, of the particle of water with respect to the horizontal plane of reference. And I said, I assumed that the particle of water is fixed, not moving, because if it's moving, you should add the kinetic component here. But we are dealing with a kind of process where water is moving very slowly. So let's forget about the kinetic component. This is also the assumption that is done when modeling groundwater. The Darcy law neglects the kinetic component. I assume from now that you know the Darcy law, which is the laws that describes the movement of water in saturated soil. Of course, you don't remember Darcy law, but this is not a problem. Let's just remember that the Darcy law describes the movement of water in saturated soils. It's a very simple law that you for sure studied in your basic hydrology course. I assume that you remember just this, that the Darcy law, when I speak about Darcy law, I'm talking about, again, the law that describes the movement of water in saturated soil. Here we are describing the movement of water in unsaturated soils. So it's a different situation. We cannot use the Darcy law. Okay, as I said, you define the energy of this particle of water but by just specifying the altitude with respect to a reference horizontal plane. In this case, we have to add the capillary forces which give additional energy to the particle of water. Let's indicate with psi the capillary forces. Okay, they can be estimated. There are some indication on the literature for estimating the capillary forces depending on soil type and especially soil porosity. And keep in mind that the capillary forces depends on soil moisture. The capillary force, besides then depending on the soil behaviors, also depend on theta. Because if you get a soil that is saturated, then the capillary forces are zero. Because, as I said, capillary forces develop at the interface between water and air. When you get to saturation, you don't have air anymore, so there is not this interface, and the capillary forces are zero. This is a basic difference with the Darcy law. Darcy law doesn't consider capillary forces. We are describing the movement in an unsaturated soil. We have to consider capillary forces. By the way, maybe that in your basic hydrology courses you already dealt with this theory I'm explaining now. Maybe if you are lucky, and but usually I would say no. But at the end of my explanation, I will ask you. We will make a pool. Okay. So the energy is given by this quantity here. At this point, we can apply the Darcy law to compute the velocity of water migrating in the downstream underground direction. And let me now write the Darcy law. remember. I turned it on. Yes.
Yes.
Sorry. So let's write that Vz, because as I said, this is a monodimensional movement, and therefore I'm just considering one component of the velocity, the one in the z direction, in the vertical direction, is equal to minus, because I assume that z is positive upward, water is moving downward, so minus k. K is a constant which is called hydraulic conductivity, and it's a constant, typical constant of the Darcy law. It's a parameter which depends on the soil and especially the porosity of soil, and this constant multiplies the derivative with respect to z of capital H, the energy. This is the Darcy law, which is very simple. You get water moving by spending energy. In this case, if you have a decrease of energy in the downward direction, then this energy is employed to give velocity to water in the downward direction. So it's very simple. And the relationship between the gradient of the energy and the velocity is linear through a constant, which is called hydraulic conductivity. This is Darcy law, very simple to understand. And why it's linear? Because usually, you know from hydraulics that the relationship between the energy gradient and the velocity while water is moving is non-linear. It's quadratic typically. And it's quadratic because you consider also the kinetic component of energy. If you neglect the kinetic component, because you assume that the flow is very slow, then you get a linear relationship. And this is confirmed by experiments that Darcy first made in laboratory. Okay, so this is a very simple equation, but in this case, we have to substitute for capital H the sum of what? So Wz equal minus k, derivative with respect to z of, in this case, let's write H plus psi. Now, Vz is equal to minus k, which multiplies the derivative of h with respect to z is 1. If z is positive upward, the derivative is 1. So I can just write minus k, and again minus k, and now I have to take the derivative with respect to z of psi, or psi, I don't know how to pronounce in English, let me say psi. And given that psi depends on the soil, but for a given soil depends on soil moisture, let me to put in evidence this kind of dependence. So I write minus k, which multiplies the partial derivative of psi with respect to theta times the partial derivative of theta with respect to z. And let me write it in this way. Vz is equal to minus k plus a quantity that I indicate with the symbol capital D, which multiplies the partial derivative of theta with respect to z. And in practice, D is equal to k times derivative of psi with respect to theta. And keep into account that usually this derivative in textbook is represented as a total derivative, because many authors assume that psi depends only on theta, because theta explains for an assigned soil, for a fixed soil, much of the variability of C. So you can also find this derivative in total terms, not partial terms. But in any case, when we write D for this D, what is? It's a peculiar behavior of the soil. You can find tables giving to you for reference soil types suggesting D values. So let's consider it a parameter in a way. Okay, so keep this relationship in evidence because we need it later on. Okay? Now, we have a problem here that we have two variables, two unknowns, theta and v. So this equation is not enough. We have to introduce another one. And I already applied conservation of energy. The logical choice for a second equation is conservation of mass. Because of course you have mass conservation in the groundwater. When you fix a control volume, an appropriate control volume, you can apply conservation of mass of water here, of course. Okay, let me delete everything in the blackboard but this relationship, and we try to keep it. And now let me apply the conservation of mass. Let's refer to an assigned control volume. Let's assume that we identified a control volume. Typically, if you want to describe infiltration in a portion of soil, the logical choice for the control volume is to get a volume that is delimited upward by the soil surface, downward by an impermeable layer, if it exists, and laterally by making some assumptions depending on the purpose of your application. Okay? And when you identify a control volume in practice, you have to always take into account that you can take your control volume without any constraint, but you have a necessity. When you apply the Reynolds transport theorem, you have to integrate the equation, as we will see, and you need to specify initial and boundary condition for the control volumes. So when you select a control volume, it's much better to get, for instance, an impermeable layer down in the downward direction, because it's much easier to specify initial condition and boundary condition at the impermeable layer. Because, of course, the impermeable layer, you can say that no water goes through it. So it's an ideal situation. The boundary condition is already specified. When you have to apply the conservation of mass, if you are able to select a control surface such that you don't have any passage, any exchange of mass through this control surface, is perfect. Because it means that you don't have to specify the fluxes of mass through the surface, which is for the boundary condition. Instead, if you take a control surface that is permeable, in order to compute the mass balance in your control volume, you have to specify the exchanges of mass through the control surface. This is quite intuitive. If you have this volume and you want to apply the conservation of the mass of water here, if you select the boundary so that some water can get through the boundary, you have to specify this flux of water entering the boundary, and this is the boundary condition. Instead, if you can select a boundary that is impermeable, this is perfect. This is the reason why very often we adopt the watershed as control volume. Because in the watershed, do you remember the definition? We can easily define the water inflowing is just rainfall. If you remember how the watershed is defined, you have just an inflow of water which is given by rainfall. So this is perfect. You don't have to describe water flowing in the underground inside your watershed. So even in this case, I want to describe the filtration. We don't have, in order to derive the theoretical development, we can say that the control volume is assigned in whatever way. We can not care about it. But of course, when we want to apply filtration models in practice, we have to define the control volume. So the better thing would be to take a simple control volume. If you have, again, an impermeable layer in the deep ground, let's take it as limit of the control volume. This is just something that I wanted to mention to you, because I will not ask during the examination to you how would you take a control volume. This is not a question for the exam. But I just would like to make clear, and it's not easy in English, in Italian would be much easier, that very often we speak about control volumes, boundary condition, and we don't understand what is the practical meaning. The practical meaning is very simple. Boundary condition means water. If you want to compute the mass balance, you have to know the water flowing into the portion of space in which you are applying the mass balance. It's very simple. But often we forget, because we speak in mathematical terms, and even derivatives, integrals, they have a very easy to understand, I would say, practical meaning, but often we forget. Just integrals, we associate the word integral with something that is boring and nasty, and I speak for myself, maybe that you are very passionate about mathematics. I'm not, and therefore we forget about the practical meaning. So let's go back to our necessity to compute the mass balance. You remember that I introduced the Reynolds transport theorem. This is a circumstance where I make use of the Reynolds transport theorem. It's very simple to write the mass balance. We have a control volume. We can write the mass balance in this way. Let me write and then I explain. We have an integral applied to the control volume. An integral of what? The product of the mass